Today we're going to be learning how to take the derivative when we have multiplication or when we have division, right? It's called product rule for the multiplication, quotient rule for the division. Be really careful. It's not super easy, right? I really wish that if you have some multiplication like f times g, I really wish we could just take the derivative of the first, f prime, times the derivative of the second. I wish I could just take the derivative of each piece and then multiply them, but that's not how it works. If it was that easy, we would have been doing this rule with the stuff we did last time. There is a rule that works for all these products, all these multiplications, but it's not super easy. It's not super apparent. It's not that simple. Same thing is going to be true for the quotient. Whenever I have division, I really wish I could do the derivative on the top and then just divide it by the derivative at the bottom. I really wish it worked that way. If it was that easy, we wouldn't need these specific rules for it. It would be like the addition and the subtraction rule that we did last time. Instead, we have these much harder rules. Product rule is going to be okay. Quotient rule is going to be harder. But we do have these rules that work 100% of the time, every single time. And you're just going to have to memorize them. So however it is, y'all memorize stuff, you're going to need to memorize these, right? It's not super straightforward. It's not ideal for how we would kind of prefer them to be, but it is what it is. Let's go for it. Here we go. I've got derivative of f times g. Don't remember this in terms of f and g, because later on it may not always be f and g, but think about it more as being you have a first function and you have a second function, right? And if you think about it in terms of first and second, it doesn't matter if it's f and g or if it's h and k or if it's L and op. It doesn't matter, right? First and second is always going to be applicable when you have multiplication. So let's do it. You're going to need the derivative of the first times the second plus, not done yet, plus you need the derivative of the second times the first. Okay, again, the derivative of the first, so if your first was f, derivative would be f prime, times the second, so whatever that function was, you just copy it, plus, then you have the derivative of that second piece times the regular first. Okay, so it's a little bit strange. There is some wiggle room, right? Because this is multiplication. You could change the order. You could do g times f prime. That doesn't matter. Same thing here. You could do f times g prime. You could even change the entire chunks, right? You could take this, move it first, that, move it second. Because of the commutative property, you could change and you could rewrite this in different orders and it would all give you the same answer. The idea, though, is you need one function's derivative and then the other regular function. And then in the second chunk, I would need the second derivative and then the first regular function, right? You should have one's derivative with the other's regular in each of the two chunks. You can't have an f prime also attached to an f. You can't have a g prime attached to a g. You have to have kind of one derivative and the other regular function. And again, don't remember this as f prime g, g prime f, because later it may not be f times g. Later on, it could be h times k. And then if you have it memorized in terms of f's and g's, later when you hit h's and k's, it may not work, right? So remember in terms of first and second, and then no matter what those individual pieces are labeled as, f, g, or whatever, you're going to be good to go. Derivative of the first times the second plus derivative of the second times the first. However y'all memorize stuff, you need to memorize this product rule. Let's practice. Here we go. I've got multiplication, first chunk, second chunk, so I can use my product rule. Let us go for it. The derivative of this first would be 3 minus 4x. So I take the derivative of that first piece. Now I'm just going to copy the second. So derivative of the first times the second. You don't do any work, you just copy. Plus, then you're going to need the derivative of the second times the first. A lot of the times I just do the copying, because you don't have to do anything for it. So derivative of the first times the second, which you just copied, plus the derivative of the second, which I will now do is just 4 times the second. So all you had to do is copy. All right, now you could leave it like that, or you could like multiply it out to reduce it. Let's multiply it out. You'd have 15 plus 12x minus 20x minus 16x squared. Oops, I forgot the whole other piece. That's silly. And then you have a plus 12x minus 8x squared. So we could simplify this let's see, we have the x squared, so we got a negative 24x squared. Got an x, an x, an x. So let's see, you got a 24 minus 20, so it looks like a plus 4x, and then you just had the 15. So you could simplify the derivative and kind of get it expanded, looking like a polynomial. You really didn't have to. You probably could have just left it, right? The question just said find the derivative, so you could have stopped right here. That would be fine. You took the derivative. That's all the question said. It didn't say find the derivative and simplify. It just said find the derivative. So if you were to stop there, that's fine. If you wanted to simplify, you could do this. Now, let's think about something conceptually. Here, if you really wanted to, you could have avoided the product rule. It would have involved some extra algebra, but you could have avoided it. How? You could have just taken all of this, and algebraically you could have just FOILed that stuff. You could have just distributed. You could have just multiplied the original function all out. Right? Let's do it. I think here we'd have, 15x plus your 12x squared minus 10x squared minus, let's see, we got 8x cubed. So you could have rewritten this original function. I think that's the only one, minus 8x cubed. Then you have those two, which would combine. I think that would just be a plus 2x squared plus 15. So without doing any calculus, you could have just put in some algebra legwork, and you could have rewritten this original function as so, and then if you have it as a polynomial where every term is just a power term, then you could use the power rule, right? The derivative of negative 8x cubed is negative 24x squared. The derivative of this middle piece is here. The derivative of 15, oops, I forgot that x, didn't I? 15x. So you could have multiplied it all out and then taken the derivative, or you could have taken the derivative and then multiplied it out. Either way, you should get the same answer if you all simplify to the same spot. So that one, yes, you could have avoided the product rule if you had done the algebra to multiply it. That would give you the same thing as doing the derivative, then multiplying it out, right? You kind of end up at the same location. Let's go to the next one. There's really nothing algebraically you can do because you have trig. So you're just going to have to do the product rule. So let's go for it. Here, this first one, you have 2x and then a cosine. So just a product rule for this first left piece. The derivative of the first would be 2 times the second, cosine, plus, I need the derivative of the second. The derivative of cosine, we did that last time, was negative sine, times the first. So all of this, right, this product rule, I've expanded it all out. And now let's think about this next one. And let me try to explain something to you. If you wanted to do product rule, you could. It's not really wrong. You don't have to, but you could. If I wanted to consider the negative 2 as the first chunk and the sign as the second, if you wanted to do product rule, here's how it would be, right? The derivative of the first would be 0 because that's a constant. The derivative of the first times the second plus the derivative of the second times the first. When one of the two terms is a constant, half of the product rule ends up canceling, and then you just end with the negative 2 cosine, which if you just knew, hey, negative 2 sine, I know the derivative of negative 2 sine. You can kind of just copy the negative 2, and then the derivative of the sine is the cosine. If one of the two terms in your product is a constant, you don't have to do the product rule because the derivative of the constant is going to be 0, so half of the product rule is just going to cancel. If you have something like 5x squared, you could do product rule between the 5 and the x squared, but the derivative of the first is going to be 0, so half of that product rule is 0. If one of them is just a number, you could just kind of take the derivative using your power rule, and you can jump straight to the answer. So be careful. You don't have to do product rule when one of the chunks is just a number, right? If it's just a coefficient. It's whenever both of the chunks have a variable, that's when you must use the product rule. Anyways, let's simplify this. You have a plus 2 cosine, then you have a minus 2 cosine. So those actually cancel. That's lovely. Then you have a minus 2x sine of x. That is what the derivative simplifies down into. Okay, hopefully that makes sense. If not, go back and rewatch it or go YouTube some extra practice problems. But product rule needs to be in your toolbox from now on out. Let me try to get this underneath the screen. Okay, quotient rule, again, it would be so lovely. My life would be so much easier if we could just do the derivative on the top divided by the derivative on the bottom. But unfortunately, that's not how it works. This is going to be even worse than the product rule, so brace yourselves. Here we go. Again, don't remember it with F's and G's. Remember it in terms of top and in terms of bottom. Right? For multiplication, there's always a first and a second. For division, there's always a top and a bottom. So here we go. This is how I remember it. Derivative of the top times the bottom minus, different than the product rule, minus derivative of the bottom times the top. Wish we were done, but we're not. Over the bottom, so whatever was there, squared. It's a really ugly rule, but that's one you're going to have to know. Let's go through it again. The derivative of the top times the bottom minus the derivative of the bottom times the top over the bottom, so whatever's on the bottom, over the bottom squared. One more time, just for funsies, okay? Derivative of the top times the bottom minus the derivative of the bottom times the top over the bottom squared. Don't remember it with F's and G's because it won't always be F's and G's. Remember it in terms of top and bottom. You'll be a little bit safer, right? Now, remember I was saying there's a lot of wiggle room with how you can write the product rule, but I always like to write it like this, so that way there is some consistency with the quotient rule. Yes, you could still, in the quotient rule, you could still change the order of those chunks. Am I making it more? No, I'm making it more slanted. Sorry. Trying to fix it, but I'm not being very successful. Okay, so you could flip this order, but you really shouldn't flip the order because it's subtraction, right? And the order for subtraction matters. So I always like to write it like this and like this. That way there's some consistency, because what do you notice about the numerator of your quotient rule and then your product rule as a whole? Well, they're almost the same thing. It's just the operator. For product rule, you have a plus, and then for the quotient rule, you have a minus, right? This, the top of the quotient rule, and then the product rule, they're conjugates of each other. So there are some similarities, and then quotient rule, you have to do over the bottom squared. So there are some similarities, but they're definitely not super enjoyable rules. I wish it was more straightforward. I wish it was super simple, like, hey, just do the derivative first times the second, you're done. Or, hey, I wish it was take the derivative of the top and the bottom, and then you're done. I wish it was that easy, but it's not. But you know what? We'll all live, right? We'll all live. We'll be okay. Okay, let's do a couple of examples in practice with this quotient rule, because it's a nasty formula. You really need to practice, because this isn't going to get in your brain without some dedicated practice. Okay, here we go. We do have a quotient. Very nice. Let's go ahead and use the quotient rule. Derivative of the top times the bottom minus the derivative of the bottom times the top. All of that's over the bottom squared. Okay, let's see if we can simplify this. Again, it just says find the derivative, so you don't really have to do anything more. But if you wanted to simplify, here's how it could. You have x cubed cosine x minus 3x squared sine of x over x cubed squared. Multiply, that would be x to the sixth. And it does look like that one's got 3 x's, that one's got 2 x's, that one's got 6 x's. So it looks like you could reduce everything by x squared. So here you would still have x cosine x minus 3 sine of x over x to the fourth. That's as reduced as you could get it, canceling as many x's as possible. You can't go, oh, I'm going to cancel 3, and then cancel 2 and have 1 x on the bottom. No, you have to reduce everything by the same amount of x, right? And then you only reduce by the least amount of x's. Okay, let's move on to the next one. Here we go. We got derivative of the top times the bottom, just copy, minus the derivative of the bottom times the top. Then all of that would be over the bottom squared. I'm not going to bother simplifying it. I'm going to leave it like that. That's fine. I don't really care. It's important that you just know the rule, and then if you had to simplify it, yes, I could distribute, maybe I could combine some like terms, but this one's not going to really get that much nicer, so I'm just going to leave it. Okay, so remember, product rule, derivative of the first times the second plus derivative of the second times the first. Quotient rule, you have the derivative of the top times the bottom minus derivative of the bottom times the top over the bottom squared. If you were here in class, I'd make you repeat it with me a couple of times to hopefully get it stuck in your head, but you're not, so, I hope you just do it at home. Okay, let's look at this one. If you have a quotient rule in which the numerator is a constant, it may be easier to skip the quotient rule. And then if you can rewrite it, it may just be easier to rewrite it and then do the power rule. So something like 9 over 5x squared. Without doing any calculus, you could just algebraically rewrite that as 9/5 x to the negative second power, right? The x squared on the bottom is the same thing as having an x to the negative second power on the top. And if you rewrite it like this, again, you don't have to do product rule because one of the terms is just a number. Half of the product rule would be 0. Here, if you could rewrite it as a power term, you could just do the power rule. Okay, so here I have 9/5, and then that -2 is going to multiply to the front, and then it's going to decrease by 1. So here I think I'm going to end up with -18/5 x to the -3rd. That would be fine. Or if you wanted to, you could rewrite it like this. Okay, doesn't matter. I'm okay with this. Or you could put it with the x cubed on the bottom, either way. But always keep an eye out for when sometimes a little bit of algebra on the beginning, on the onset with the original function, a little bit of algebra makes your calculus life easier, right? And if you can avoid the quotient rule, I would probably suggest that you do so. So just be careful. Okay, next, we're going to actually prove some trig derivatives. We're going to prove the derivative of tangent and the derivative of secant. You could also prove cosecant and cotangent. I'm not going to. They're similar. They're just a little bit different. But here we go. These proofs would need quotient rule. But now we know quotient rule, we can do it. Okay. Remember, tangent is the same thing as sine over cosine. And then now that we know quotient rule, I can take this derivative to get the answer. So let's do it. The derivative of the top times the bottom minus the derivative of the bottom times the top over the bottom squared. Okay, so I used quotient rule. Got it. Cosine times cosine is cosine squared. Negative times negative is going to cancel, give you a plus sine squared. Come on, pencil, come on. Plus sine squared over cosine squared. And then you should hopefully know from your Pythagorean identities that cosine squared plus sine squared, that's just 1. And then 1 over cosine squared is secant squared. Sorry, my computer just made a little noise at me. It distracted me. Okay, so here we go. The derivative of tangent is secant squared. Little bit annoying. You could always reprove it if you want. The proof involves quotient rule, but you should know quotient rule. But no, you don't have to keep redoing it. It's kind of just another one of those facts that you should have memorized. The derivative of tangent is secant squared. The derivative of cotangent would be similar, except your sines and your cosines are switched. And so here you would actually end up getting negative cosecant squared. So remember, all of the cofunctions, I kind of mentioned this last time. Let me write it again. Remember, the derivative of sine is cosine. The derivative of cosine is negative sine. So you should have really all 6 of your trig derivatives here together. Any trig functions that starts with the c, all of the cofunctions, when you take the derivative, they are going to be negative, right? And then the cotangent is similar to the tangent, except your sines and your cosines are switched. So instead of it having a cosine squared on the bottom, this one would have ended up having a sine squared on the bottom, and it would have picked up that extra negative also. Okay, let's go through and do secant, and then the cosecant would be really similar. Here we go. Let's rewrite secant as 1 over cosine. So let's do this derivative. The derivative of the top times the bottom minus the derivative of the bottom times the top over the bottom squared, right? So 0 times cosine is 0. Then you have those two, which are going to cancel, which is why these end up being positive. So I've got a sine. And then instead of cosine squared, check this out. I'm going to break it up. I'm going to do cosine times cosine, right? You could, like, leaving it as sine over cosine squared, that's not wrong, but it's going to be a little bit different way of writing it that I think is a little bit easier. Right, so here we go. Check it out. I have sine over cosine squared. I'm going to group this in such a way so that I have 1 over a cosine, which is secant, and then I have sine over cosine, which is tangent. So the derivative of secant is secant times tangent, secant tan. Right, let's fill in the box. Secant tan. A little bit annoying, but again, just remember it. You'll be okay. The derivative of cosecant would be similar, right? But instead of it being positive, it's going to be negative. All of the cofunctions have a negative in the derivative. And instead of it being secant tan, it's going to be cosecant cotangent. Okay, so there you have it. There, now we all know all 6 of the trig derivatives, so we should be covered for whatever it throws at us. Let us do the next page and a half, which is going to get us some more practice, and then we'll pause, we'll end this video, and then the next one we'll pick up with composites and the chain rule. Well, let's practice, let's speed through these. Again, product rule, quotient rule, examples. Here we go. First chunk, second chunk, the derivative of the first times the second plus the derivative of the second times the first. Again, derivative of the first times the second plus, I did the derivative of the second, and then I just copied the first, and I moved it out to the front so it would look a little bit nicer. Okay, next one, we have a quotient rule. This one, I kind of had to, I just put the divided by bar, so if you need to, you could rewrite it. Okay, let us go for it. The derivative of the top is just 1 times the bottom minus the derivative of the bottom would be negative cosecant cotangent, right? So the derivative of the bottom times the top over the bottom squared. And this would, obviously, that's just going to be 1, and then those two negatives are going to cancel. Honestly, I don't care. You can just leave it like this. I'm going to throw down, it does simplify a little bit. I don't really care, honestly, if you simplify a lot. You're not going to see stuff like this very often. Again, here's the quotient rule that I just did. You could kind of distribute this stuff and then simplify and reduce it as much as possible. You can pause if you want. I don't really care, though. I'm just going to leave it like this. Right? I just said find the derivative. I found the derivative. Now I'm done. Let's move on. Okay, now these are good questions, right? This is very nice, quasi-abstract, because you don't actually know what the functions are. It just kind of names them. You got g times h, and then it just tells you some pieces of information about g, g prime, h, and h prime, right? So these ones seem like they're hard, but actually they're easier, right? If these types of questions, once you get the hang of them, they're actually pretty simple. So let's go for it. It says here's f, which is g times h. So f is some product. And then it says find the derivative of f at 2. So I know to get from f to f prime, I would have to take the derivative. And I know since f involved multiplication, taking the derivative of f is going to require a product rule. So let's go for it. Again, if you remembered f prime g, g prime f, now you'd be screwed because it's not f's and g's. The f is there and the g is there, but really your multiplication is g times f. So you remember it in terms of first and second, and you'd be a lot better suited. I have the derivative of the first times the second plus the derivative of the second times the first. And then no matter what they were, h and g or element op, it doesn't matter. You're going to be good. Now let's plug it in. We wanted f prime of 2, so change all the x's to 2's. I need g prime 2 times h of 2. Then I would need h prime of 2 times g of 2, right? Just change all the x's to 2's. And now I just have to go find what those 4 numbers are and then plug them in. Let's go for it. It's all kind of handed to me on a silver platter. G prime of 2, it told me, was -4. In the question, handed it to me. H of 2 was -1. Then I need h prime, which was 5. And then I need g, which was 3. So this one seems strange because you don't know what the g or the h function is. You only have some very specific information about it. But that actually kind of makes the question easier. You just do the derivative rule, plug in the values where they're supposed to be. Here I have 4 plus 15. So this answer is smelling like a 19. So without ever knowing anything about f or g or h, I can tell you that the slope of f when x equals 2, the slope of that graph is going to be 19. So if I drew a tangent line, the slope of the tangent line would be 19, right? Or the instantaneous rate of change would be 19. You can do this derivative even when it's more abstract. Just follow the rules, plug and chug. The next one's going to be more or less the same thing, but instead of just presenting you all this list in all this information in a list, or sometimes they may organize this data in a table, right? So sometimes they'll just give it to you in this list. Other times they'll take that same information, put it in a table, or other times they'll give you that information in a graph. Okay, but we can still do questions like this. Here, again, I have h, which is f times g, product rule. Then here I have f divided by g, quotient rule. So let us go for it. First thing is always just to write out your derivative rules. Derivative of the first times the second plus the derivative of the second times the first. Wonderful. That's the derivative rule. Next thing you need is h prime of 1. So change all the x's to 1s. F prime 1 times g of 1 plus g prime 1 f of 1. Now I just need to go get those 4 values somehow from the graph, and then I'm going to be able to get this answer. Okay, f prime 1. That means the slope of f when x equals 1. So make sure you go to the f function and you're going to count the slope of f at 1. Here's f. F starts on the bottom, crosses over. It's kind of like the less bold one. So here's the point on that graph. Can you guys count the rise and the run? Can you count the slope of that little line segment? Looks like it's going up 2 over 1, up 2 over 1. So the slope right here of this f segment, the slope is 2. Okay, now when it wants f of 1, that's not asking for the slope of f, right? F prime is the slope of f. This is just asking for the y-coordinate. So let's see, 1, 2, 3. Looks like f of 1 is up at 3. So if you're pulling an original function's value, you're just getting the y-coordinate. If you're pulling the derivative value, you're pulling the slope of that graph at that point. Okay, so be careful. Let's do the rest of these. You need g prime and you need g. Let's go for it. G of 1. Here's the g function. G of 1 is also right there. It just happens to intersect, and it also happens to be a height of 3. That's coincidental. That's okay. And then I need the slope of the g function, right? G prime of 1. I need the slope of g at x equals 1. Here's that line segment. The slope of that line segment is -1. So to pull the derivatives, you're looking at the slopes of those graphs. To pull the originals, it's just the y-coordinates. Then I have 6 minus 3, and you could get this answer. Okay, seems hard, but it's actually pretty okay. 2 more examples, then we're done. Good job hanging in there. I'm trying to go fairly quick, but not be reckless. Next one is a quotient rule example. So just same process. It's just going to involve quotient rule. Now here's a pro tip. I'm going to kind of instead of doing the derivative rules with x's, I'm just going to leave it blank because I know eventually I would change the x's to 6's. So instead of having to write the same thing twice, I'm just going to leave the parentheses blank, and then I'm going to fill them in with the 6's. But I'm still going to write out the derivative rule. Here we go. Derivative of the top times the bottom minus derivative of the bottom times the top over the bottom. So it would be g over the bottom squared. So you could put the x's and then you could rewrite it all with the x's being changed to 6's. But here I'm just being a little bit lazy. I don't want to write it all twice when I could do it all at once, right? The derivative of the top times the bottom minus the derivative of the bottom times the top. All of that's over. Whatever was on the bottom is still on the bottom. It's just now squared. So now I need to go get these 4 numbers in the top and then also that number in the bottom, and don't forget to square it. Okay, so let's go for it. 6. 1, 2, 3, 4, 5. Here's 6. Let's get all the stuff for the f function first. So here's the point. So f of 6 is going to end up being 2. So let's plug that in. F of 6 is 2. Yep, there we go. And then, let's see. We need the next one. Oh yeah, F prime. Sorry, I lost my train of thought totally and completely. That is my bad. And also, you know what I just realized? That's not even the F function. That's the G function. So be careful. Be careful. That was my bad. Sorry. The F function's up here. Here's the F function. F of 6 is 4. That's totally my bad. I was looking at my answer key. I was like, why is it different? Okay, because I got the functions crossed. That's stupid. Sorry guys. That was Mr. Bell being dumb. The F function up here, count it. It's up at a height of 4. So F of 6 is 4. Sorry. F of 6 is 4. At least I caught it now instead of having it be an issue later. That's okay. Let's now get also the slope, right? Here, the slope of that line, F prime of 6. Now that I'm actually looking at the correct line, F prime of 6 looks like it goes down 1 over 2, so it looks like it's a negative 1/2. So F prime is a negative 1/2. And then let's go get the stuff about G. And G is actually this one, the more bold one, the one on the bottom. Color coding them probably would have been smarter, Mr. Bell, but you're silly sometimes. That's okay. G of 6, that's the value, that's 2. So that plugs in actually 2 different spots. And then you need to get the slope of the graph at that point, G prime of 6, and that one looks like it's a negative 2. So again, the derivative functions, you're pulling the slopes at those points. Make sure you're on the correct graph. The original functions, you're pulling just the y-coordinates. Also remember to be on the correct graph. All right, that's good. Here we go. Negative 1 plus 8 over 4. So it looks like 7/4 is your answer. One more question for product and quotient. Then I'm done. So close to being done with this video. I mean, I get tired of making these videos. I get more excited about them being over than you do probably. I don't know. You guys are probably ready for this video to be over, but that's all right. Find the points where the graph has a horizontal tangent. Remember, horizontal tangent means the derivative must be 0. Horizontal line means the slope of that line is always 0. Therefore, the derivative must be 0. So 2 steps. Take the derivative and set the derivative equal to 0. I guess 3 steps. Solve for x, right? Take the derivative, set it equal to 0, solve for x. Let us do it. Here we're going to need to do quotient rule, but that's okay. We now know how to do it. All right, derivative of the top is 3. Derivative of the top times the bottom minus the derivative of the bottom times the top. All of that's over the bottom squared. Okay, let's simplify. I've got 3x squared minus 6x squared plus 4x over x to the 4th. Combine some like terms. So I'm going to have a negative. How about we just write it as 4x minus 3x squared over x to the 4th. And then you could reduce everything by an x. So I have 4 minus 3x over x cubed. So there's your derivative function in its simplified glory. And then what you would need to do with that derivative is just set it equal to 0. Once you set it equal to 0, you're really not worried about the denominator. You just need the top to be 0. So here the x, I think it's going to be 4/3. Remember, the graph, or this question, it didn't just ask for the x value. It didn't say, hey, find the x value where you have a horizontal tangent. It wants the whole coordinate point. To find the y value, you would just take this x, plug it in to the original equation, and you would end up getting 9/8. I'm going to skip that work for now. But if you're concerned about it, I'll put it underneath the doc cam in just a second. But in order to find the y-coordinate, you would just take your x, plug it into the original. Again, here's that work, right? Taking your x value, plug it into the original, you would get 9/8. Just remember, if the question wants the point, give it the whole point. If it only wants the x value, you can stop with just the x value. Okay, product rule and quotient rule, I know they're not nice. They could be much worse. And at least those rules, they do work 100% of the time, every single time. So even though those rules are annoying, it's still good that we have them. So yeah, just get them in your brain. Practice, study, memorize them, flashcards, whatever you do, get those things memorized.